So we're starting in chapter 8, section 2. And um, so we're in 8.2. And this is what we're supposed to get out of it. The distribution of a sample proportion, right? We don't describe a sample distribution of a sample proportion, and we're going to compute probabilities of a sample proportion, right? We looked at in 8.1 with sample means, right? Okay, so the mean of the sample, and now we're looking at proportion of it. All right, so if you think about it, there were some problems that we kept saying proportion and the had to do with the probabilities, how you expressed them as proportion or as the mean or of a proportion type thing. So just kind of remember that, and we'll kind of go from there. So, all right. First things first, for an estimate of a population proportion, suppose that a random size of size n is obtained from a population in which each individual either does or does not have a certain characteristic. Okay, the sample proportion, denoted p hat, is given by p hat equals x over n, right? So how many you have over the number that you have, right? And the n would be the sample size, where x is the number of individuals in the sample with a specified characteristic. So the sample proportion p hat is a statistic that estimates the population's proportion. Okay, it estimates the population's proportion. Now, with that being said, that little bit, they'll either give it to you or they'll give you a certain amount out of the total population, right? What your sample size is out of the population. So just know that we'll calculate that. So here's an example in a Quinnipiac University poll conducted in May of 2008. 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. 349 responded yes. Obtain a point estimate for the proportion of the registered voters who approve of the way that George W. Bush is handling the economy. Well, there's 349 of them that approved out of how many? 1,745, right? So that would be the sample's proportion, p hat, 0.2. Okay. All right. Any questions on that? Okay. Now, we're going to look at another example. This is using a simulation to describe the distribution of a sample proportion. According to a time poll conducted in June of 2008, 42% of the registered voters believe that gay and lesbian couples should be allowed to marry. Describe the sampling distribution of the sample proportion for the sample size n equals 10, 50, and 100. Now, this particular example is only going to re-emphasize that as the number in the sample gets larger, that the overall distribution of it becomes normal, right? Whether it's skewed left, skewed right, or you know, it's centered, it's still going to become normal as the number of samples goes up. And what we're going to look at is exactly that. The top left is 10, the top right is 50, and you can see the difference in those. You can, from going from top left to top right, it on top right at 50, it gets more normalized, and then with 100, you can really start to see how it's normalized, right? And the standard deviation ought to start to decrease, right? And that's what we're seeing. Standard deviation of 0.16, 0.072, and then 0.047. So as the number of the sample goes up, the standard deviation, the variability of it will start to go down. Okay, that's two characteristics that we should see out of that. Any questions on that? Yeah.
Okay, so 42% registered voters voted that. So would that be 42% out of the N? Like on the previous one?
So the question was, which one was it? Oh,
That's the ideas of, like, would that be 42% out of 10 and then 42% out of 15?
yes. Well, let's look. 42% of the registered voters, right? Now, 42% of the registered voters of who? The entire population of the United States, right? 42% of it. And we're pulling a smaller sample size to see how our smaller proportion compares to the big population itself, right? So would it be 42% of 10, 50, or 100? No, it's 42% actually goes to the total population, right? So, all right, key points to take away from those graphs. As the size of the sample N increases, the shape of the sampling distribution of the sample proportion becomes approximately normal, right? So we said as the sample N increases, the shape of it becomes more normal. We said that just a while ago. The center, the mean of the sampling distribution of the sample proportion equals to population proportion, okay? And the spread, the standard deviation of the sample distribution of the sample proportion decreases as the sample size goes up. And those are things that we looked at, right? So, all right. So let's look at a sampling distribution of p hat. For a random sample size of n with population proportion p, the shape of the sampling distribution p hat is approximately normal, provided you can use a normal approximation, provided if n times p times 1 minus p is greater than or equal to 10. Okay, so n is the number, p is the probability of success, right? A percentage, right? So 42%, that would be your p, right? 42% say that. And then 1 minus p, right? If it was 42%, then it would be what? 58, right? 0.58. So those numbers multiplied have to be greater than 10 for you to be able to apply the normal distribution on it, okay? All right. The mean of the sampling distribution p hat is mu p hat, which equals the p. So again, it's just re-emphasizing that p hat is mu p and it's equal to the p of the population, right? So standard deviation of the sampling distribution of p hat is standard deviation of p hat is square root of p times 1 minus p. Well, I say it's q, right? I tend to do this. So I tend to say, okay, it's p times q over n, and that's a q. And what is q? Q equals 1 minus p, right? P is the probability of success, right? Q would be the probability of failure, right? The complement of that. So you can replace 1 minus p with q, and I will in some of these, right? The model in the previous slides requires that the sample values are independent, right? When sampling from finite populations, the assumption is verified by checking the sample size n is not more than 5% of the population of the big N, right? So if you think about, if we're looking at 10, 50, 100 people compared to the population of the United States, a voter population, right? Then that is way below 5%, right? So regardless of whether n times p times the q is greater than or equal to 10 or not, the mean of the sample distribution is of p hat is p, and the standard deviation is the square root of p times q over n, right? So any questions on that? Right now it's just a bunch of theory, right? Until we start to use it. So let's start to use it. example 3, describing the sample distribution of the sample proportion, right? According to a time poll conducted in June of 2008, 42% of the registered voters believe that gay and lesbian couples should be allowed to marry. Suppose we obtain a random sample of 50 voters and determine which voters believe that gay and lesbian couples should be allowed to marry. Describe the sampling distribution of the sample proportion for registered voters who believe that gay and lesbian couples should be allowed to marry. So the first things first is this. We got to make sure that we understand that N of 50 is way smaller, right? Way smaller than 5% of the population, right? Y'all agree? Of the registered voters, 50 people, not even a drop in the bucket, right? Now, we also got to do this. N times P times Q, that has to be greater than or equal to 10, right? If we do that, then we can do a normalized type approach to it. So it's 50, right? 50 times probability, the P is 0.42, and then the Q is 0.58. Is that greater than or equal to 10? So when you do that, you get 12.18 is greater than or equal to 10. So yeah, we can do a normalized distribution on this. We can treat it as though it's normalized because it's greater than or equal to 10. Okay? Now, so what is the mean? Right? 0.42, right? P is equal to P hat, which is 0.42, right? We saw that where? Right here? All of that, right? So, and then if we have to do standard deviation of P, that's equal to P times Q over N. And we'll do that. That would be 0.42 times 0.58 over 50. Yep. When you do that, you get, let's see. I left my hat off right there. Boom. That gives you a 0.0698. Okay. So what does describe the sampling distribution of the sample proportion? Well, it has a mean of 0.42, right? It can be normalized because it was greater than or equal to 10. The MPQ was. And then 2, the standard deviation is 0.0698, right? So that is a distribution, or describing the distribution of it. We're not doing anything. We're not staking any claims to it yet, right? Not at all. Okay. So let's look at this. Here's everything that I just found here, right? Now let's use it. According to the Centers of Disease Control and Prevention, 18.8% of school-age children aged 6 to 11 were overweight in 2004. Okay. Now, what do we got to do with that? One, we got to make sure it says in a random sample of 90 school-age children, ages 6 to 11 years, what is the probability at least 19% are overweight, right? Probability at 19% are overweight. Well, we first got to do this. We got to check it, right? We got to check NPQ to see if it's greater than 10. So N is how many? 90. P is how much? 0.188, right? And then what is 0.188, 1 minus that. 812. It is 812. Yeah. Okay. Is that greater than or equal to 10? Well, you should come out with how much? 13.7. Is it greater than or equal to 10? Then yeah. All right. So we know that we have if we look at this, we got a mean of how much? 0.188, right? And then we got to find its standard deviation. Well, let's find its standard deviation of p hat, right? That would be the square root of n time, not n, p times q over n. Well, p is 0.188, 0.812, all over how many? 90. And that would be the square root. So what does that leave me with my p hat? Should leave me with 0.0412, right? Y'all agree? So worst case you're going to have to find is you're going to have to find the standard deviation of p hat. All right. We can say the mean of p hat there as well. So we're not done, because what is the probability that at least 19% are overweight, right? So if you kind of look at this, (19), which is 0.19, is over here, right? Somewhere over here. We're wanting to find out all this area, right? At least means 19.9 or 0.19 is the bottom end of your limit, right? So we're wanting to find this. There's a mean. So if we were to look at it, we could do a normal CDF, right? A normal cumulative distribution function, right? And you have 4 parameters. Y'all remember the 4 parameters? The first one is, what's the left limit? Nope. We could do -1e99 and then go up to the 0.19 and grab it and then go 1 minus it if we wanted to, right? But we also could just start here and go which way? To the right. And we could do that, right? So there'd be, my left barrier would be 0.19. Then I'd have 1e to the 99, right? Then what's my mean? 0.188. And then my standard deviation is this. Now, when I plug that into the calculator, I should get 0.4806, right? Yeah. Why am I not using 0.185?
Yeah, like with what we did last class or whatever.
Oh. All right. So that was 7.4. 7.4 was doing a normal approximation on a binomial probability, right? Okay. So that's kind of looking at a binomial probability. Now, and we done the distribution of a sample means, which is 8.1. Now we're doing the distribution of a sample proportion. So 8.1 and 8.2 go together, right? So, but it was when you get to a binomial probability, because it's a histogram, then you use the 0.5s, right? Okay. Normalizing a binomial probability would be the 0.5s have to come into play. Good question though. And I would highly recommend, let's see, how many we got on here now? All right, we got 9 of y'all. Let's see. Oh, cuss. All right. So I would make a go through each section and kind of pull out keywords of what things are and what formulas you use and what functions on the calculator you'll use. That would be very beneficial for you to do. Yeah, that's the only way you can kind of keep it straight, right? Yeah. Oh, you ain't seen nothing yet. You ain't even seen anything yet. We're gonna get there. All right. So you could do this with the lower bound being 0.19 and everything to the right, since we got a lower and upper, right? Or you could do the -1e99 up to 0.19 and then subtract it from 1. They'd still give you the same answer. Now, the 0.4806, what does that mean? That's the area on the curve. It's the probability of the sample proportion, right? So 48%, we would say that 48% of the sample, the 90 school age sample of 90, that would be at least 19%, or that they would be overweight, right? From that claim. All right, so let's do part B. Suppose a random sample of 90 school-age children aged 6 to 11 results in 24. Okay, so note that in part A, they gave us 19%, right? That's p-hat, right? But look in B, they're giving us an X value, right? Okay, so if we were to look at this, let's kind of go ahead and it's a little bit easier just to do this from the worked out example. But we've got p-hat is 0.2667, right? Okay. Now, that 0.2667 happens to be on that curve, the curve that we just showed right here, with a mean of 0.188, it's over in here, right? It's over in this side. Yeah? It's going to be above the mean. It's going to be above what we're looking at right there. So we got a p-hat. So we could still do exactly what we've done before, because we're looking at results in 24 overweight children, right? So we're still looking at it as a normal CDF, right? We've got, okay, what's my lower boundary? So that should be 0.2667, 1e to the 99. And then, of course, we still got our mean, right? And then our standard deviation. And when you do that, you get 0.0281, right? Which if you do that, it's about 2.8%, which you could say is 3. So we would only expect to see 3 samples in 100 resulting in a sample proportion of 0.2667. 3 in 100 resulting, right? Or results. This is unusual because the true proportion is, guess what? 0.188, right? Just means that the mean of it ought to be a little bit bigger for it, because it's unusual. They've got some bad data. Okay. Now, let's go look at some homework. And the first one we look at is just, it's fill in the blank, right? The blank denoted p-hat, the sample proportion denoted p-hat, is given by the formula p-hat equals x over n. X is a point, right? N is the number of sample, where x is the individuals with a specified characteristics in a sample of n. So really it's just drop down, plug in, right? So let's kind of look at this next one. because really these are the two calculations you're going to have to do. So describe the sample population or sample distribution of p hat, assuming that the size of the population is 30,000. N, the sample size is 300, and the p is 0.1, right? So if we look at that, n is less than 5%, and the n times p times q is greater than 10. I mean, we could do that, right? N is what? 300 times p is 0.1 times 0.9. Is that greater than or equal to 10?
Mm-hmm.
Yep, sure is. Okay. So that calculation, that's how you do that. Now, determine the mean of the sampling distribution of p hat. Well, the mean of the sample distribution of p hat is equal to 0.1. The mu of p hat is equal to the p, right? All right. Now, determine the standard deviation of the sampling distribution. That's only a calculation. And we can get to that calculation pretty easy. So standard deviation of p hat is equal to the square root of p times q over n, right? So that is the square root of 0.1 times 0.9 over how many? 300, right? So that, if you do that calculation, you should get 0.173, 0.173, sorry. And they only wanted the 3 decimal places, which would be 0.017. If you think about what we did on the 8-1, where we had the sample proportion of sample means, right? There was a calculation for standard deviation of the sample mean, right? There's same as this. It's a different calculation, but, right? It's still a calculation that we can do. All right, any questions on that? Y'all good? All right. So on these, I got tired of reading and just started clicking. So according to the study, the population or proportion of the people who are satisfied with the way things are going in their lives is 0.74, right? So P equals 0.74. Suppose that a random sample of 100 people is obtained. So out of that first sentence, we get this. Now, we know that Q better be how much? 0.26, right? That's the proportion of people that are not satisfied with how things are going in their lives, right? So suppose that a random sample of 100 people is asked, are you satisfied with the way things are going in your life? Is the response to this question qualitative or quantitative? The response is qualitative because the responses can be classified based on the characteristics of being satisfied or not, right? All right. Explain why the sample proportion p hat is a random variable. What is the source of the variability? Well, the source of the variability is going to come from, well, we calculated the variability in the standard deviation, but the source of variability in this study would be the sample proportion p is a random variable because the value of p hat varies from sample to sample. The variability is due to the fact that different people feel differently regarding to their satisfaction, right?
So, like, depending on how they split up studies or do studies, there could be multiple people that market.
If you do, like, if you repeat this,
Each trial will have a different map.
but as a whole, they should all mimic back to the proportion of the whole population
Okay.
that it's.
So to do that, you have to have some sort of test.
Yeah, you've got to go through So the real key about this is you got this huge population, right? You can't go and question everybody. So you pull a sample, right? And you're doing iterations of that sample, right? And the more you get, the more true to the population that it should reflect, theoretically, right? And it will.
So even if they have different p-hats and stuff, they can, or proportions, they can all be combined onto one.
Now the means should be what?
This-
Same. Right. Now would it move just a little bit? Yeah, but not much, right? You could be a little bit off on the mean, but it ain't going to change like the standard deviation is going to change, right? As your sample size goes up. The mean's going to vary just a little bit from a small sample compared to a huge sample. But it should mimic around the mean of the population as a whole.
But we're predominantly just gonna be dealing with like one p-hat question.
Yeah, yeah. All right, so those are theoretical. So now we're getting to the meat and taters of it, right? What the heck is going on here, right? So now we're going to, according to the proportion of people who are satisfied with the way things are going in their lives is 0.74. Well, we said that was P, right? That's the mean. And then Q would be 0.26. And we know that N is what, 100? So if we do this, we do NPQ, it's got to be greater than 10. Describe the sampling distribution of p-hat, the proportion of people who are satisfied with the way things are going in their life. Be sure to verify the model requirements. Since the sample size is no more than 5% of the population, and population being who? Everybody. Everybody, right? N times P, 1 minus P, which is actually Q, is 19.24, right? If I would take N, P, and Q, multiply them, I get 19.24 is greater than 10. So we can look at this in a normalized distribution. The distribution of p-hat is approximately normal with the mu of p-hat of 0.74 and the standard deviation of 0.44. Well, the only thing that we had to kind of calculate is this, the standard deviation of p-hat, which is p times q over n, which would be the square root of 0.74 times 0.26 over 100. And if you do that, you should get 0.0439. And if you round that to 3 decimal places, you get 0.044, right? So again, the only things that we're having to calculate is they gave us the mean, right? P, right? So we can find the standard deviation of p-hat, right? In the sample obtained in part A, what's the probability that the proportion who are satisfied with the way things are going in their life exceeds 0.76? So if you look at this, if you draw this, the mean is 0.74, right? Here's 0.76. Exceeds, we're looking this way, right? From 0.76 to the right. Do y'all see that? Okay, so that's going to help me when I do my normal CDF because I can go, okay, I can start my limit where? At 0.76. You see what I'm talking about? That little bit of pictorial graph there of that bell shape of where things are and what I'm looking for is going to help me set things up a lot easier. So I'll go normal CDF, right? Because it's cumulative. I want everything underneath it. So 0.76, comma, 1E99, right? My mean is 0.74. And my standard deviation, I'm using 0.0439. I'm going ahead and taking it out to that 4, right? Because I calculated it 4, even though my answer only wanted 3. Y'all with me? Now, when you do that, what it's going to give you is this. "32% of the population are satisfied with the way things are going." Right? All right. Any question on that? Let's look at the bottom. Using the distribution from part C, would it be unusual for a survey of 100 people to reveal that 68 or fewer people in the sample are satisfied? 68 or fewer, right? Well, they didn't give me a P, a mean, right, or percentage. They gave me an X, right? So I got to do P hat, right? So my X happens to be what? 68 over how many? 100. So that's 0.68, right? Okay, if you look at it from the graph, 0.68 is on this side of the mean, right? And we're saying reveal that 68 or fewer, right? So that's everything to the left. Y'all with me? So if that case, then we should know that a normal CDF, we should have what? What would be our left limit? -1e to the 99 up to how much? 0.68. You've already got the mean in there, right? And the standard deviation. So there you go. That should give you 0.0859, right? I write that a little bit neater. Is it? It's no, 0.08% is greater than what? 5%. So it's not unusual, right? 0.0859, which is not unusual because the probability is not less than what? 5%. If it's less than 5%, it's unusual. Well, what does that mean? It means the likelihood of that event occurring is really, really low, right? You could just about disregard that event happening. That's why they consider it unusual, right? All right. Any questions on that? Starting to make a little bit more sense? Do you see this, how this problem was set up? They went over some theory. Then they gave you a mean of P hat, right? Which was a percentage, right? A proportion, right? A proportion is a decimal percent. Then we had to work it out, right? Then they turned around and said, here's an X, right? Now go do it again with an X. So that's the only thing that they've done with this problem. They gave you the two variations of inputs that they could give you and said go, right? Y'all understand? Excellent, good. Because that's about as hard as it gets. Now, suppose a random sample of 1,000 is obtained from a population whose size is 1.5 million. Well, 1,000 is far less than 5% of the population, right? So we're good on that, check. And whose population proportion is specified characteristic of the mean of P of 0.54, right? A mean proportion of 0.54. Calculate part A through C. Well, we know that the mean of P hat is 0.54. It says describe the sampling distribution. Well, we do that with the mean and the standard deviation. We did that on problem number 2 like that, or example number 2, did we not? We calculated the mean and we looked at the mean and we calculated the standard deviation of P hat. So first things first, we got to find the standard deviation of P hat, which is P times Q over N. Well, P is what? 0.54. Q is what? The complement of that, right? Which would be what? There you go. Over how many? 1,000, right? So what does that give me?
Wait. Oh, okay.
0.0158, right? Yes, it does. It do. It do that, right? Yeah, it do. All right, good. Don't try to figure it out. It'll be okay. All right. So we found at least our two things that we can need to go to work on, right? Those are the two things we need. Now they just got to either give me a X value or a proportion of it, right? So what is the probability of obtaining 570 or more individuals with a characteristic, right? Or with this characteristic. So how do we figure that out? Well, 570 is not a proportion, is it? 570 is what type of value? It's an X, right? So we can find p hat as being X over what? N. So p hat for this would be 570 over 1,000, which is going to be what? There you go, 0.57, right? Yeah. Now I've got p hat and I've got the standard deviation of 0.0158. I can go do this. Probability that it's greater 570 or more, right? So let's think about this. The mean, if we draw this, the mean was 0.54, right? Boom. And 0.57 is here, right? They're wanting to find out this, correct? Area to the what? To the right. So do you know how to set up your normal CDF? Yeah. Piece of cake now, right? You see how that little drawing is going to make your life a little bit easier? Normal CDF, so we'd say, okay, 0.57, 1e to the 99, that's our upper limit, right? Comma, the mean is 0.54, and then we have a standard deviation of 0.0158. When we do that, ladies and gentlemen, we should get 0.0288. Okay?
I'm really confused how you're being able to put so many numbers into your normal PDF. When I'm able to do it, it just
No.
gives me trials.
No. I'm on CDF, not PDF.
Oh, sorry.
Number 2, not number 1. There's 2 normals. Normal PDF is the exact value. Number 2 is normal CDF, which is cumulative distribution function, which is what we predominantly been using after we got out of chapter 6, right? 6 or beginning of 7, somewhere around in there, right? Yeah. Because when you talk about from up to that, at least that or less than that, then you're talking about a cumulative, all that area underneath, right? Does that make sense now?
Yes.
Okay. All right.
So, sorry. How do you know when to put IE99 for the upper versus the lower?
You see this graph? So I
So
put,
if we're trying to find everything above 0.75, it's in the upper category.
not 0.57, right?
Oh, yeah, sorry.
Yeah. So this would be your lower limit, and this would be your upper limit, right? This is your mean of p hat, and then this right here would be your standard deviation of p hat. Okay, then my lower limit right here would be 0.57. What's the biggest number up here? Well, that's infinity. So how do I put infinity? 1e99, right? And how do I get an e? That is the little button above what? Right here. Second comma, right? Second comma.
Okay.
Yeah.
Thank you.
You're welcome. All right. So I'm just going to set this one up. We'll, for sake of time, because we're kind of this is what's the probability of obtaining 520 or fewer, right? So it's from 520 or fewer. So we're looking at, so if you look at, that's again an X value, right? So P hat equals X over N, plus 520 over 1,000, which is 0.52. So we're looking here at 0.52. So we're looking at all this area over here, right? So if we were to set that up, it'd be a normal CDF. The lower limit would be -1E 99 up to what? 0.52. And then, of course, your mean is 0.54. Standard deviation is 0.158. Ladies and gentlemen, when you calculate that, you get 0.1028 all day long, right? Okay. Now, any questions on that one? So this problem had calculate the standard deviation, right? And then here's two X values. One from there and above, and then one from X value and below, right? Okay, no big deal. And then this one, well, they gave us a sample size of what? 150. They gave us a P of 0.6, right? So the N is 150. Again, the N 150 is less than 5% of the 30,000, right? And then the P is 0.6. So that means a Q is what? 0.4, the complement of it, right? So if we do this, we know that it's approximately normal because NPQ is greater than or equal to what? 10, right? So you can calculate that. 0.4 times 0.6 times 150 should be, and I don't have that calculated. 0.4 times 0.6 times 150. That's 36, right? It's 36 greater than or equal to 10 all day long, right? So we can say it's normally approximately normal because of the sample size less than 5% of the true population, and then the NPQ is greater than 10. The mean is 0.6. That's P, right? Yeah. So they didn't give us no X value, did they? Where we had to find P hat. They gave us the mean of the population, which is the same as the mean of the proportion, right? Y'all with me? All right. So the standard deviation is set to 6 decimal places. So do you know how to go change your calculator to 6 places? Mode, go down to float, go over to 6, hit enter, right? Yeah. Mode, go down to float, right to 6, hit enter, boom. All right, but we're going to find, P times Q over N, right? So that would be 0.6, 0.4 over 150. And ladies and gentlemen, this comes out to be 0.04 with rest of them zeros, right? You're going to put it out 6 decimal places. Your numbers may generate numerics that are not zeros. Fair enough? Now, we've got standard deviation and we've got the mean of the population. What is the probability of obtaining X equals 99 or more, right? With the characteristics. X equals 99 or more. What's the first thing I got to do? I got to find my P hat, right? My P hat is 99 out of what? 150. They didn't give me a percent, did they? All right, they didn't give me a percent. They gave me an X value. So that is what? 0.66, right? It's got to be greater, 99 or more. So if you look at that, you know, your mean is what? What did we say our mean was? 0.6. And then we're here. So it's 0.66. and then we're looking this way, right? Once you draw that, you should know I got 4 things, 4 buckets to fill in. What's my left bucket? Normal CDF, that's right. 0.66, right? What's my second bucket? 1E 99, right? Again, how do I get the E? That second comma. That's that little button above the 7, the comma. Now, what's my mean? 0.6, and then my standard deviation. For this one, I can just go to, it's not going to change it, right? When you do that, guess what you get, guys? 0.0668, yeah? Which is 6.68%. So out of 100 repetitions of this, we would expect 7 to be 99 or what? More, right? Okay. Questions on that? Okay, that's 8.2. So chapter 8 is the sample means proportion and the sample proportional mean. Well, the sample proportion, right? The probability of sample mean is 8.1 and the probability of sample proportion is 8.2. All right, so make sure you get those. If I was creating a sheet, I would make sure that I had chapter 8. Here's the topic. Here's my formulas. Here's what I'm looking at. Boom. Sample mean, sample what? Proportion, right? Okay. All right. So now we have done all these things, right? Now we're about to get into chapter 9 when the fun begins. 9, 10, and 12. Okay? It's crazy. It's good stuff, though. All right? So we're going to look at estimating the value of a parameter. That is really chapter 9. So estimating a population proportion. We're going to obtain a point estimate for the population's proportion, right? We're going to construct and interpret confidence intervals for the population proportion. We're going to determine the sample size necessary for estimating the population proportion within a specified margin of error. Okay, so we're going to end up calculating a lot of stuff. Okay, and there's certain Z values for the confidence interval that we're going to look at that would be for a 90, for an 80, for an 85, a 90, 95% or 99% confidence interval. Okay, so as we do these, you can kind of write them down, create you a table yourself, and it would help you. Now, before I get into this, let me say one thing real quick. All of your homeworks are now back open, and they close on 12/7. Now, it's 12/7 because that's the last day of class, right? I have not got the day of our final for stats yet. Yes, it should be online. So I'm 99.9% confident, right? That it's going to be online. I just don't know whether it's going to be on Pearson or on Blackboard. The platform is the only thing that they haven't told me, but I've asked. Okay. So let's look at chapter 9. We're going to look at confidence intervals. Okay. We've looked at what we're going to learn. Now, point estimate, P hat, X over N, right? Anything new on that? No. So if we look at this, calculate a point estimate for the population proportion. The Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed death penalty for persons convicted of murder. 1,123 were in favor. So if we were to look at the P hat of that, right, the point of estimate, it would be 1,123 over 1,783. It'd be a proportion, right? 0.63. Fair enough? All right. So nothing that it kind of leads right on into where we're doing, right? Now, confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. Fair enough? So the level of confidence represents the expected proportion of intervals that would contain the parameter if a large number of different samples is attained. The level of confidence is denoted 1 minus alpha times 100%, right? For example, a 95% level of confidence, alpha is 0.5, implies that if 100 different confidence intervals are constructed, each based on a different sample from the sample proportion or population, we will expect 95 of the intervals to contain the parameter and 5 not to contain it. Does that make sense? So if we were to pull 100 samples of it with a 95% confidence, we would say that 95 of them would contain what we'd want, and 5 would not. If we said we had a 95% confidence interval based on some X value, right? Some parameter. The parameter is going to control your confident interval, right? The level of confidence. As far as what's your interval going to be, lower and upper, right? So let's go. Confidence intervals estimates the population proportion are in the form of point estimate plus minus a margin of error, right? The margin of error of a confidence interval estimates a parameter is a measure of how accurate the point estimate is. The margin of error depends on 3 factors. The level of confidence. As the level of confidence increases, the margin of error also increases. They're directly related. Okay, direct correlation there. The sample size. As the size of a random sample increases, the margin of error decreases. Well, that would make sense, right? As your sample gets bigger, your error ought to get smaller. And the standard deviation of population. The more spread there is in the population, the wider our interval will be for a given level of confidence, right? The more spread, the more variability of our data, the wider of an interval we'd have for a confidence, right? Confidence interval. Any questions on that? A lot of theoretical stuff. Now, look at standard deviation of p-hat. Look at that. We've seen that again, haven't we? Right? So p times q over n, the square root of that, right? As long as the sample is less than 5% of the population, right? Right? All right. Now, interpretation of a confidence interval. A 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of a simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. Constructing an 1 minus alpha times 100% confidence interval for a population proportion, suppose that a simple random sample of size n is taken from a population. A 1 minus alpha times 100% confidence interval for p is given by the following quantities. Lower bound is p hat minus z of alpha divided by 2. All right, it's the confidence interval divided by 2, right? Well, I say the alpha, it'll be what's on the outside of that confidence interval, okay? So if we were to look at, and we say, okay, let's say that this is a 90%, right? Correct? 0.9. Then we have over here, how much is left over here? Huh? We have a total of what? 0.1. If we divide that by 2, well, if we do 0.1 divided by 2, what do we get? 0.05 over here, and how much over here? 0.05 over there, right? That's our alpha, right? Now, our z alpha divided by 2 right here. We're going to find that, right? That's how much is still left underneath the curve, right? That's an area. Do y'all understand that? So if that's an area, this Z is an area. So if I draw this right here and I do that, then this area is 0.05. Then I can do an inverse norm of, guess what? Of the area, right? This is going to be area. And we can say a mean of 0 and a standard deviation of 1. And that will give us, guess what? Our Z. This little calculation right here. If we were to draw this, we got a 90, 95, 80, 85, whatever. We split to put equal portions on each side, right? We just need that area and put it right there in an inverse norm, which is number 3, right? That'll give us our Z value. Y'all with me? Okay. We know what p hat and 1 minus p hat is. That's p times q over n. This is the standard deviation, right? So we've got all these components that we can find now. Y'all agree? So we're going to be able to do a lower bound and a what? Upper bound. It's great. It's wonderful. Now to find that z-score without having to go and look at a table, inverse norm, right? You got the area, you want a z-score for it, boom, right there. Mean of 0 and standard deviation of 1. Now, margin of error. That's that z-score, right? Times the standard deviation. Of the alphas divided by 2, right? The alphas are the ones that are above it, right? Okay. Now, these are just formulas, so just make sure you kind of rock along with me. So let's look at this one. We'll go back to the same thing. 123 were in favor of the death penalty out of 1,783, right? We got a p hat of 0.63. And when we do this, we say, okay, we can normalize. We can do it with a normal distribution, right? Because the n times p times q is greater than 10. All right, so we've got to find, we could find the, let's see, we want obtain a 90% confidence interval, right? So right here, this is 90%, right? Which leaves us 10%, right? So we've got 5% over here and 5% over there, which is how much in area? 0.0 what? That's right. Now, you see this 1.645? If you were to go look at a z-table of 0.05, you would get 1.645. You would get that. But I don't want to take the time to go look at a table. I can do, let me do it real quick. I can do second vars. Well, I got to clear ink. All right. I can do second vars, and I can go down here to number 3. Now, this one has the updated software, right? Where it says left, center, or right. Okay. You know what the really cool thing about this is? You could tell it has an area of 0.9 and tell it it's the center, and it'll automatically do it. It's pretty cool. Anyway, but it's 0.0 what? 5. Boom, boom, boom. Left, right. Negative 1.6449. That would be the lower one. What would be the one for the upper one? Positive 1.6449, right? So what did we get over here when we did this? What did I tell you we'd get? 1.645, right? So if you round it to 3, you get that, right? So you don't have to go look at a table. You can calculate that on the fly. You just draw it. You just understand, okay, that's my area that I got to go look for right there, right? And it's inverse norm 0.05, 0, and 1, right? That gives me this. 0.63 minus, boom, is 0.61, and then upper bound would be what? It's a straight calculation. So a 90% confidence interval means that we would have from 0.61 all the way up to 0.65. Out of 100 samples, 90 of them would fall in between that. Fair enough? That's what it's saying. 10 of them wouldn't, right? Okay. Now, can you do this? Can you do the upper and lower on the calculator? Sure enough, you sure can. You ready? This is pretty cool. Pretty cool. Now, I'm going to tell you, you got to find the area. You got to find the Z, right, of the alphas, right, or sub-alpha, whatever you want to call it. The area of that is not within the confidence interval. So, let's go. All right, let's go here. All right, so I want to go stat, and I want to go over here to test. Okay, if you got a confidence interval, you're going to go stat test, and that's where you're going to look at it. And if you got hypothesis testing, that's where we're going to also go. Now, how do you decipher between the two? If you've got a confidence interval, it'd be an INT. If it's a test, guess what? Hypothesis testing, it'd be a test, right? So if we go down, it's not this one, okay? And it's not this one. It's not number 5, a one proportional Z test. That's for hypothesis, right? We need to go all the way down here to guess what? A one proportional Z interval. That's a confident interval, right? Watch this. Boom. What's our X's? What did it say our X was? Did it say? 1,123, right? Boom, boom. Out of how many? 1,783, right? Boom. A confidence interval, how much? 0.9, right? All right. Calculate. Boom. Look at that. 0.611 to 0.6486, right? If you round to 2 decimal places, guess what? We got exactly what we just calculated, did we not? Okay, so you got a calculation that shows you how to do that by hand. Lower bound and upper bound, right? Okay. It's always going to be your p hat minus the Z alpha, sub alpha, times the standard population, right? Plus and minus that, right? Okay. So there you go. Stat test A. We're doing that one proportional Z interval, confidence interval, right? Y'all with me? All right. Now, so here's hat by hand, and we've shown you how to do it on a calculator. Ain't that sweet? We're 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of the murder is between 0.61 and 0.65. A proportion, which means the number divided by the what? Total population, right? Oh, how about that? Would fall 90% of them, right? Yep. Sweet. Okay. Now, sample size needed for a specified margin of error, E, and a level of confidence. The formula uses p-hat, which depends on n, the quantity we're trying to determine. 2 possible solutions. Use an estimate of p based on a pilot study or earlier study, right? N is the number of things that you want for a sample, right? Or let p equals 0.5, which gives the largest possible value of n for a given level of confidence and a given margin of error. So if they ever give you something without a p-hat, or confidence interval of it, or point of it, then you've got to use p-hat of 0.5, right? No point of interest is used. Use a p-hat of 0.5. Just remember that. That's going to come in handy. All right. So the sample size required to obtain a 1 minus alpha times 100% confidence interval for P with a margin of error is given by P hat times Q, right? 1 minus P hat's Q, times the square of the Z of the alpha, right? Divided by the E, the margin of error. That would tell us our sample size, right? Round up to the next integer, where P hat is a prior estimate of P. So if you don't have a prior estimate of P, what do you use for P hat? 0.5, right? So we'll give you the largest sample and what? What did it say? Largest sample. Largest possible VN for given and what? Given margin, right? So it's going to give you the largest one you can have. All right, so it's taking everything into account. All right, round up to next, right? So a sociologist wanted to determine the percent of residents of America that only speak English at home. What sample size should be obtained if she wishes her estimate to be within 3 percentage points of a 90% confidence interval? Assuming she uses the estimate obtained from the Census 2000 supplementary survey of 82.4%. That 82.4% is what? Your P hat, right? Okay. Now, we have an estimate of margin of error of 3%, right? Within 3 percentage points. That's 0.03. Y'all with me? Now, you see this right here? The 1.645? That's a Z for a 90%, a 90 confidence interval, right? So if I were you, I would do like 90 of confidence interval. A Z is 1.645. And then I do one for 95, one for 99. I just kind of do those and find out what they are, right? You could quickly, I mean, it ain't like, this would be 0.05, right? 05, right? 005, right? 0.05. This would be 0.025, right? Putting the area underneath, right? And you can find it in inverse norm. I would find those Z's so I wouldn't have to go calculate them anymore. Once I've done it one time, I just have it written down, right? Does that make sense? So, and if you look at it, you can always, you know, confidence interval, Z values for confidence intervals. You can pull it up, it'll have it, and you could already have it, right? So here's P hat, 0.824, right? 1 minus P hat's Q, and then 1.645 over 0.03 squared gives us 436.04. So we need a sample of 436.04, but it said do what? Round up to the next integer, which would be what? 437. So a sociologist must survey 437 randomly selected American residents, right? So that would tell you what your sample size has to be based off your confidence interval and your margin of error. Fair enough? Now, that's all chug and plug. I haven't been able to find that on that calculation on the calculator to do it by hand. I mean, as far as to plug stuff in and boom, there it is. Okay. Not saying that it's not there. I just ain't looked for it. I figured, okay, you could P hat times Q, right? Q hat, right? This is P hat. Z sub alpha, right? Over the E squared, right? All that. So there. That's as far as we're going with that. And we're actually done with the content itself. We just need to do what? Do them homework problems, right? So 98% confidence interval. Boom, boom. That means 98% is in here, right? Right there. How much is still left? 2%, right? Which would be 1% over here and 1% where? Which is what? 0.0 what? 1. So if we go, what's the Z value for it? We could click up on that right there. standard normal go 0.01, we could find it, couldn't we? Yeah, we sure could, and do it. Just do it for, to be able to go, okay, I can read it and do it. But I would also do it on the calculator, right? Inverse norm, 0.01, 0 mean with a 1 standard deviation. Ladies and gentlemen, 2.33. Okay?
So we wouldn't put it in as a negative.
No, you wouldn't. No. You're looking at the area. We know that it comes out, if it's negative, it means it's below it, right? It's below the mean, right? So that is symmetrical about the mean. So it'd be positive. We're just doing the positive ones, right? Now, on this right here, you could have said, guess what? 0.02 divided by what? You could have put that in there. Okay? And it would calculate it, that 0.01 for you. I think if you do a graph like this, a normal curve, and do it, and do percents, and then change those over, you'd be okay. Fair enough? So 2.3, I'd go out to, well, this said the 2, but I'd do so I'd have a 98. I'd go out to 4 decimal places for Z for 98 confidence, right? We got a 90 and 98, 95 and 99. You're going to see them. Then a blank is the value of a statistic that estimates the value of a parameter. Point estimate is, right? Okay. Any questions on that? Anybody? All right. Now, construct a 99% confidence interval of the population proportion using the given information. They gave us an X value. They didn't give us a mean, did they? So what we got to do? Woo, P hat. 120 over what? 200, right? What do we get right there? I jumped the gun. Yeah, sorry. We get what now? 0.6, right? Now, we need standard deviation, do we not? Standard deviation of P hat is what? Square root of P times Q over what? N. So that's 0.6 times 0.4 over how many? 200. What's that? What do we get? Not 0.12. I got that. 4.6. It's got to square root that thing. All right. So, now, and we can do it, right? You can do this, right? It's P hat minus the, well, we got to do what's the Z? What's the Z real quick? The Z of a 99 would be what? We're looking for a Z of what? 0.005, right? What is that? That'd be inverse norm of 0.005 with a 0 and a 1, right? What does that give me?
How do we have 0.005?
Like when you draw out the
99%. So that leaves 1%. So that'd be 0.5 over here, and then 0.5 where? Over there, right? Which is 0.005, right? Yeah? So if we were to do that, inverse norm of that would be second bars 3, right? That'd be a 0.005. You don't have to worry about the mean and the standard deviation. It's already set as 0 and 1 in there. Hit enter, guess what? That is 2.5758. So for 99% confidence interval, there's my Z. I'd write that down, right? Because that way I wouldn't have to calculate that anymore, would I? So if you were looking at this, if we were to look at the lower bound, Okay, that's p hat minus z alpha over 2, right? Times what? Standard deviation of what? P hat, right? So that would be 0.6. I'm only going to do one of these, then we'll plug in the calculator. 0.6 minus 2.5758 times 0.0346, right? And what you get is 0.5109 if you do that calculation, right? Y'all with me? So can you calculate the lower bound and upper bound by hand? Yeah, it's not that much. It's not that bad of a calculation. But do I need to? What do I need to go to? Well, we got a 120, right? Let's see, it's 120 and 200, right? And a 99, right? So let's go over here. Let's go stat. Let me hit clear real quick. Boom. Stat test. And then we're going down to which number? A. 1 proportional Z interval, right? We're going to hit enter. We're going to say, okay, 120 is our X, right? Out of how many? 200, right? And we want a confidence interval of what? What did it say? 99. So that's what? 0.99. Hit enter. Enter. Boom. See this right here in parentheses? 0.5108 and 0.6892. That's your lower bound and your what? Now, what did we calculate? We calculated 0.5109, didn't we? We gonna be all shook up for 1/10,000th? Not in my life, I ain't. Right? All right. So we can do that very quickly in the calculator, right? But we can also do it by hand. Y'all with me? But you got to know how to do it. Okay? That's the key important thing. All right. Anybody got any questions? Somebody got their microphone on. So, all right. It's off now. Okay, let's look at the last problem, and then we're going to go because it's already time to go anyway. So you give me this one last problem, and then we're good. Because we've got to find the error. And Lord have mercy, we've got to do this by hand, so we might as well just do it, right? So a researcher wishes to estimate the proportion of adults who have high-speed internet access. What size sample should be obtained if she wishes to estimate to be within 0.05 with a 99% confident interval? A, she uses a previous estimate of 0.54. Okay, so let's see what we're talking about right here. Okay, we list this out, and then life will become a little bit easier, and we'll be like, okay. So here's A. So we've got what? E is the error of margin, right? Is 0.5, right? 5%, right? 0.05, right? Now we also need a Z. What's the Z of a 99? I'm doing Z99 to CI, right? Nope. 2.5758, right? Did we done calculate that one time? Yes, we did. See how these right here? I put the Z of 99 CI, right? Z of a 99 confidence interval. Y'all see what I'm talking about? Most people go alpha divided by 2, right? But some I'm used to that. Okay, now P hat is 0.54, right? Boom. So P hat's 0.54. Q hat would be what? How much? 4.6, right? Yeah. I transposed that on my notes. It's Q hat because we're talking about P hat, right? Yeah. All right. So what is this? Let's see if we can do this. The N is equal to P hat times Q hat times standard deviation of P hat divided by E what? Squared. So we've got 0.54, 0.46, and no, it ain't standard deviation. My bad. My bad. I should just, this is my Z, right? Of my 99 confidence interval, right? CI, right? Boom. So that is 2.5758 divided by this. Boom, squared. Ladies and gentlemen, when you do this, you get N is equal to, get what? I don't know, because I calculated it, but I don't know. I wrote it down, but I didn't do it. 0.54 times 0.46 times 2.5758 5 squared. I get 659.22. All right. And that should go to where? 660, right? So the N should be 660. Now, what's the difference between A and B? B says she does not use any prior estimate. That means that P hat is not 0.54. The P hat now is what? No prior estimate. We have no P. The P hat is now what? 0.5. And we still got, let's see, a Q hat of what? 0.5, right? And then we're still in our squared, right? So N would be 0.5 times 0.5 times the Z interval, right? 5758 over 0.05. All of that squared. And when you do this, you get, guess what? 663.47, which is what? 664. So we have calculated confidence intervals, right? Lower bound and upper bound. We've calculated the number based off of error, margin of error. We've calculated P hats. We've calculated what? Z of alpha is divided by 2 for the confidence interval, or the Z score for it, right? So we've done a lot of stuff in this 9-1, right? So if I were you, I'd take a little sheet of paper and 9-1, and I would do a brain dump of formulas and what they mean and where to use them, right? That's going to be important because we're 9-2 and then 10, 12, done. You'll blink twice and we'll be done.
So you're allowed to like make your own formula too, make it on the self component.
Yeah,